across one of the problems in a math class where your teacher talks about somebody standing across the room walking towards the door, and they're going to go half of the distance to the door. And they make the point that as you continually go half of the remaining distance, you get closer and closer to the door. But then they make the argument that if you keep going halfway, you're never going to actually reach the door. But then you get really frustrated because you're at the door, right? Well, you might be an inch away from the door, but you're still at the door. And so in theory, we're never going to get to the door, but we are kind of at the door. And so this is where we're going to start our conversation today about limits. Okay, so limits are going to give us a way to talk about some unspeakable math, some math that's just a little bit uncomfortable to think about. In each of these three scenarios here, we have a function that is trying to get to this value L as x gets closer and closer to a. So we're going to think of a limit as the destination for the function. Where is it trying to get to as x goes to a certain number? Much like in life where we have destinations or goals that we want to get to, sometimes we don't get there, sometimes we don't reach it, sometimes trouble happens along the way. Same is true for our functions here. So we have a function that in this case on the left is equal to L at x equals a. So that's not only where the function is going to, but that's where it ends up actually making it to. So f of a, if we put a into the function, we're going to get L out. The limit as x approaches a, that's what this notation means down here, of f of x is also equal to L. On the second graph, the function is again going towards L. So if we're traveling along this red graph, we're going towards L as x gets closer and closer to a. At a, though, our function's doing something a little different here. Our function is not at L. It's defined to be this point down here that is significantly less than L. So our function doesn't necessarily have to equal what the limit is. So our function at a doesn't have to equal the limit as x approaches a. In the third case, the function is not even defined at x equals a. There's an open circle on that point. The graph is completely undefined. But again, the graph is going towards that value. So the limit as x approaches a of f of x is equal to L. So informally, we can think of limits as where is the function trying to get to. A little more formal definition from the College Board, similar to what you would find in a calculus textbook, is given a function f, the limit as f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. If the limit exists and is a real number, then the common notation is what we have here. The limit as x approaches c of the function f of x is equal to r. So very wordy, and the words here are vague, right? Arbitrarily, sufficiently, these are words that are kind of sound a little bit open-ended. If we look at an example here, we're saying that as x gets closer and closer to 3, so if we're choosing numbers like 2.9, 2.99, 2.999, or on the other side of 3, 3.0001, as we're picking values that are close to 3, we're going to get y values that are consistently close to 8. Okay, so there's a matching up that goes on. Again, this does not say that f of 3 is equal to 8. F of 3 could equal 8, but we don't know that just by seeing the limit. Okay, so the limit could be the same as what the function equals at that point, or it could be something completely different. If we're looking at this with the formal definition that we just saw, we can say that we can make the values of f of x arbitrarily close to 8 by taking x to be sufficiently close to 3, but not equal to 3. So we're getting f of x values in that range around 8 as we take x values that are close to 3. Evaluate limits two ways today. We're going to look at limits using tables, and we're going to look at limits using graphs. And we're going to deal with the algebra side in the next lesson. So Here's a problem that says guess the value of the limit if it exists by evaluating the function at the given numbers. So we are going to evaluate this limit as x approaches 5. Notice if we try and put 5 into the function, we're going to get a denominator of 0. And so this function is actually undefined at x equals 5. So we're going to go to the calculator and we're going to enter in the equation here. We've got x squared plus x minus 30 and divided by x minus 5. And we're only looking at these particular values on the table. And so we're going to go to table set and make sure the independent is set to ask so that we can put any values we want in on our table. So we're going to go second graph, and let's create this table by choosing some values we'd like to see. 4, 4.9, 4.99, 4.999. And then we have on the other side, we have 5.001, 5.01, 5.1, 6. And again, just notice that when we put 5 in, we get error because the function is undefined there. So the limit is the value that the function is approaching as x gets closer to 5. So as you see here, as we get closer to 5 from below 5, the y values are increasing and they look like they're getting close to 11. As we approach from the other side, the same thing seems to happen, except we're closing in from 12 down. It would be safe to make a guess that the limit here as x approaches 5 would be equal to 11 because it seems like that's where the values are going. Just to verify with another value here, let's throw in an extra 9. And you see that it shows up as 11 because it's rounding that 10.9999 to 11. So this is how we would look at limits with a table. If we had a function and we had some values around 5 that we could put in, we can get an idea of what that limit is going to be. Or maybe we're just given the table and we're given some values on either side of the number where we're trying to evaluate the limit, and we can do it this way. Be careful though, this doesn't always work. There are some limits that you try and do on a calculator like this and you're going to get a really bad approximation for. So for right now, this is a good strategy to use, but this is not a good long-term strategy for us when we want to evaluate. When I do a limit problem with a graph, I like to think that I am traveling along the graph heading towards a certain value of x. Now, that's kind of ridiculous, right? We can't shrink ourselves down to microscopic size and travel along the graph. So I've done something far less ridiculous over the years and created math critters to travel along the graph. Don't worry, they are not harmed as we shrink them down and move them along the graph. This year I've created a couple new guys here. Hopefully they're going to be as famous as like Pokemon. So I'm going to take this green one here and I'm going to place it on the graph. And I have a graph here of f of x is equal to sine of x over x. And I want to look at the limit of this as x approaches 0. And if you look really close here, I can zoom in with projector mode here, there is an open circle at this point here, and it looks like it's at 0, 1, but the graph is not defined at 0. Sine of 0 over 0 is undefined. So what I'm going to do here is shrink down this math critter here, and I'm going to do that reducing its size here, maybe making it a little bit bigger. Let's scale it up a little more here. And I'm going to have the center of this at f of a plus 0.5. Okay, so as I move my slider here, it's going to move my critter closer and closer to 0. I have this other one here, and I'm going to shrink this one down. And face it in the other direction. And we're going to put it on the graph at point B. So we've got B, f of B. We'll add a little bit to it. And so with this slider here, I can move that there. So as we approach 0 from the left side with this green math critter, you can see the y values, the f of x values, are getting closer and closer to 1. So that when we're really, really close here, we're at 0.993, 0.999, and it's so close to 1 here that it's just saying that it's 1. Okay. The same thing's going on as we approach from the right side. So we would call this a right-hand limit. So as this approaches here from the right side, it's walking along and it's getting closer and closer to 1 also. It's ridiculous, but it's helped students remember over the years. It's math critters and love, okay? They are both going to the same spot. If they're both going to the same location and there's a relationship formed here, then we say that the limit exists. So the left-hand limit here is 1, the right-hand limit is 1. They are both going to the same spot, okay? So the limit seems pretty safe here, that the limit as x approaches 0 of sine of x over x is equal to 1. Let's take a look at the notation for limits when we're approaching from the left and right side. So you notice here that we have the limit as x goes to -2, and there's a little exponent looking thing with a plus. So this is saying that we're looking for the limit as x approaches -2 from the right side. So we're starting out to the right of that point, and we're approaching -2 from that side. The limit as x approaches -2 from the left is written with the minus sign, and then the overall limit is just the limit as x approaches -2. In order for this limit to exist, the right-hand limit and left-hand limit have to be exactly the same. So in the previous example, our math critters were going to the same location, and so because they were going to the same location, the limit existed at that point, okay? So we're going to take a look at a graph and evaluate multiple limits based on what we see on the graph. So here's the graph that the problem was referring to. Let's start out by taking a look at the limit as x approaches 2 from the left and the right side here. So again, we've got this setup that we kind of play around with. Let's get extra parentheses in here. Shrink this down. Okay, so as we go in from the left side, if we take a look at the limit as x approaches 2 from the left, the y value that the math critter is approaching here is 4. So the left-hand limit in this case is equal to 4. As we go in from the right side, you're going to notice that it's heading towards a different value. So as we go from the right side, the right-hand limit in this case would be equal to 0. So the left-hand limit is equal to 4. The right-hand limit is equal to 0. They're going to different locations. It's a tragedy. They're never going to meet up. And so in this case, when there's a tragedy, we say the limit does not exist. There is no relationship there. That does not exist at all. And so the left-hand limit and the right-hand limit are different. If we look at -2, the same kind of thing is going on. The left-hand limit in this case would be equal to 2. The right-hand limit would be equal to 0. In fact, the function is defined here. F of -2 would actually be equal to 4. The final set of problems, we had the limit as x approaches 0 from the right and from the left. In this situation, as we approach 0 from the left side, we're going to 2. As we approach 0 from the right side, we're going to 2. The limit as x approaches 0, in this case of f of x, would be equal to 2. So left-hand limit, you are starting from the left of the point and heading to it. Right-hand limit, you are starting to the right of the point and going to it. In order for a limit to exist at a point, the left-hand limit and right-hand limit have to be the same. This is what a left-hand limit looks like as we are moving towards that point. This would be the limit as x approaches 2 from the left. And then this other one here is the limit as x approaches 2 from the right.